Welcome, everyone. My name is Adrian. I'm going to be your host for this webinar. This is the first of a series of webinars we want to do on Asset Hub and, raise awareness, talk about best practices, and also dive deep in the following webinars on certain topics, both in how they work, but also how to actually implement them, how to interact with them. So actual hands-on, look at the code, look at on-chain data, play with some tooling, all sorts of things. We'll see. It's going to be fun. In this one, the first session, we're going to focus more on the fundamentals and the theoreticals, I guess. I don't know if that's a word. And talk about the problems. So basically talk about what is Asset Hub and why it came into existence, right? And we'll discuss high level, discuss the mechanics, but we'll not probably go into the implementation details. I'm pretty sure we won't have time. I saw this session is pretty long in terms of how much time we have allotted. So I am thinking of keeping some sort of interactive format, because I'm pretty sure we have time to, even if we get sidetracked or take questions or stuff like that. So since we're going to cover a lot of topics, I think it's best if you have questions along the way, just look for a moment to cut in and we can discuss. Before we actually get started talking about Asset Hub, let's take a step out, like a zoom out, and look at the Polkadot ecosystem altogether, right? This will drive the motivation of this presentation and Asset Hub, so it's important for the context, I think. So Polkadot is one of the core differentiating factors of all other blockchains out there, is that it's a heterogeneous multi-chain ecosystem. So what does that mean? So first of all, multi-chain or multi-shard is something that you keep hearing in the blockchain space, I guess. And that comes from the need to scale, and specifically doing horizontal scaling. So there's generally two types of scaling, vertical scaling and horizontal scaling. Vertical scaling is when you do the same thing, but you do it faster and faster, right? So, how CPUs get faster in terms of frequency, that's like vertical scaling. An example of a blockchain that vertically scales or that its mission or its idea behind it is Solana, which is always trying to use better hardware, more powerful hardware, and basically scale by doing the same thing, but doing it faster. And there's a whole lot of a number of other chains that went to this horizontal scaling route. And that means instead of doing this one thing but do it fast, is doing more things at the same time, kind of parallelizing work. And we see that again in computing. You see that CPUs scaled vertically for a while, but then they started scaling horizontally as well, adding more cores, adding more CPUs, and doing parallel work. And the same thing that is happening in the blockchain space. And most chains out there have horizontal scaling in terms also known as sharding, meaning it's still the same chain, it's still doing the same thing, as in it's running the same code, the same rules, right? The same functionality, but you just vary the data that's coming in and out in these different parallel instances. So basically, you process more data at once, right? By running the same thing, but 3 instances of it at the same time, right? And we call these shards. But that's a homogeneous system. It means that all of these shards are the same. They look alike. They're doing the same thing, right? It's just different input data to them. Polkadot has a heterogeneous model, right? And it's not the only one out there. For example, Cosmos also has this, but it's the only one that has all of these things on the left side of the screen at the same time. So first of all, let's talk about heterogeneity. That means that all of these different chains, different shards are now separate chains, right? And we can call them separate chains because they are independent, and they can look wildly different. Right? Each chain can do something totally different, and basically the whole thing, instead of being homogeneous, now it's heterogeneous. It's like all different, it's that famous thing with the polka dots. Each polka dot has a different shape, size, and color. Now, though, the other thing that makes Polkadot great and unique is that it offers this shared security. So I mentioned Cosmos earlier. It has heterogeneity as well. It has app chains, but each one of these chains has its own consensus, needs to run its own validators, and basically has to figure out their own economic security. Whereas in Polkadot, all of this is shared by the entire ecosystem, and all of it is provided by the relay chain, which Gav called it recently in the decoded that just happened. The relay chain is like this massive cynical roll-up reactor. Right? So you can think of it as like a roll-up, but it's, instead of being optimistic or like hopeful, it's very cynical, and it actually checks everything, verifies everything, and offers the highest degree of like security or like integrity promises, verifications, whatever you want to call it. Now, all of these chains that are being run by the relay chain, by this massive roll-up reactor, can be wildly different because the relay chain is very unopinionated in terms of what each of these chains can do or should do. Or it only requires a very generic set of requirements. It's like you have to be able to run the code. The logic has to be able to run in a WASM VM, which is pretty flexible. WASM has a pretty big data instruction set and can do a lot of things. And it has to be able to run within certain hardware limitations, I guess. So basically, run within a certain slice of time. For example, it's like 6 seconds, right? Your block cannot execute for more than 2-3 seconds, otherwise it won't fit into the 6-second slot. And use a limited amount of memory. There's this POV, which is like a proof of validity kind of thing. I'm slowly going into all of these parallels I shouldn't be going into. But basically, where I'm getting at is you have horizontal scaling, you have app chains. We call them app chains because each chain is different. They're heterogeneous. This provides maximum flexibility to the ecosystem. You get shared security. All of this gets secured by one relay chain. All the economic power of DOT secures the whole ecosystem. And then the last part is also really cool or important, is all of these chains are sovereign. By sovereign, I mean they control their own destiny. They control their own logic, their own on-chain code, the runtime, and they govern themselves, basically, right? Polkadot allows them to do that. And all of these together have a shit ton of benefits, a lot of pros, too many to list here, but it's important, and we're going to focus on some of the challenges that come because of this. Right? Because of this, let's say, complex or powerful system, we also get challenges. So let's look at some of those. So we mentioned sovereignty. And because all of these separate parachains are sovereign, there appears a concept of trust, how to handle trust. And let me dive deep into that a bit. So on this picture here, there's like six chains, right? So we're going to talk about, let's say, A and B, Parachain A, Parachain B. Each one of these control their own runtime. That's sovereignty. What Polkadot security does, or the Polkadot shared security, it provides execution integrity. So what it does, it says it guarantees that all the blocks created by these parachains are following the code that they make publicly available on chain, that they follow that code to the letter. Right? So if they say, this is the code that this parachain does, this is what it should do, right? You don't trust entities, you trust the code, right? Polkadot security guarantees that that code is followed to the letter. If some validator, some collator, some block producer produces a block that's doing something slightly different than exactly what the code says it should do, then Polkadot will not include that block, or will not finalize that block within this whole ecosystem. So basically, it will just not include that block in the parachain, and thus not include that parachain fork in the relay chain or in the whole larger ecosystem. So basically, Polkadot offers execution integrity, but it doesn't, and it cannot, once it has given the chain its own sovereignty, it cannot handle trust. As in, it cannot impose on that parachain what it can or should do. Right? So parachain A and parachain B, if you build a cross-chain application with these two, you have to sort of trust the code on parachain A and parachain B, right? And when you build an application, you usually think about what's the interests of these parachains, right? Is my application like aligned with those interests? If it is, then I'm pretty sure that the application won't break, because those interests are the parachain's interests and they won't change, or the logic behind it shouldn't change if it's going against its own interests. But you have to think about this across things, and it becomes very important in an example, a core example of blockchains, which is basically asset transfers, cryptocurrency, or just generic virtual assets. And in particular, especially when you're doing cross-chain asset transfers. So before we move into that, I have this slide. It's not really fitting into the story, but it's really important. It offers a bit of background on sovereign accounts and what they are. We're going to be using them across this. The concept of sovereign accounts is going to be used throughout this presentation, so I have to go over them really quick. So basically, there's a picture here on the right with 5 chains, and chain A is red, and I'm showing in red on all these other chains that there is this account. It's called sovereign account of A, and it's an account that is derived from the location of A in the Polkadot ecosystem, right? And sovereign accounts are actually a better name, not necessarily a better name, but one other name for it is derived accounts, right? So they're the accounts derived from a location. Account derived from an actor, and we identify that actor by its location, by his or her its location. And then you can derive an account, a local account, based on this external location. And we call that a sovereign account because that external location has full control over this local account. So it's it has sovereignty. Again, we're using this word sovereignty, meaning that it has control over this account. So basically, chain A has this account, derived account on all of these other chains that it can control. And so it can send a message to chain B and say, do something, and it will act on, it will be identified locally by this account if you need an account for that action. Maybe some actions don't need an account. Looking at another example here, we have Bob. This time, Bob is a user, and Bob has an opened account on chain B. This is the blue bubble here. And this blue bubble is an account that Bob explicitly opened on chain B. So basically, he went on chain B with his wallet and said, generated a key and said, okay, this is my account. Bob did the same on chain A and chain E. These are the red and green bubbles. Right? These are explicit accounts opened by Bob. At the same time, Bob's account on chain B has these derived accounts on every other chain. Right? So this blue bubble here can act or do actions on every other chain, and it will do them locally through this local account, which is derived. And the last thing on the left here shows that this derivation is in the control of the chain. So basically on chain D, the chain D logic dictates or has basically the on-chain logic that dictates how derivation happens. So this derivation can happen in a number of ways. And it can even allow account collation, meaning combining two accounts that we know are equivalent. So for example, in chain E, you get this derivation where, if you say, okay, I have a location which is basically on another parachain, and then a signed account on another parachain signed by Bob. That means Bob has the private key, and that means Bob can use the same private key to control the same public key on the local chain. So we might as well just say, these two are the same account, right? So chain E decides to do that. Sovereign account of Bob on chain B is actually the same thing as Bob's local account, right? But that's just a decision that each parachain can or cannot implement. So for example, I have in chain A, in the red chain, these two are not equal. So yeah, that's a detail. But the point is, now you are in the context of one chain, and any external location can act on the local chain where we are right now, right? Through a derived account that is derived from the value of this external location. By value, I mean the description of how do you describe this location looking from my point of view, looking at this external point, right? And we have this concept of XCM multi-locations. I'm not going to go into them for this presentation. Good. Back to asset transfers. And we're talking about asset transfers and trust. When you have asset transfers on the same chain, you don't have to worry about trust. Basically, you have Alice wants to send tokens to Bob, so it just sends them. And what happens is, actually, if she wants to send 42 tokens, her total balance is decreased by 42. Bob's is increased by 42. And the total issuance of tokens doesn't change. This is important, this total issuance part. We don't want the tokens, these assets, right? I'm calling them tokens, you can call them assets, basically a representation of something. You want them to hold value. So they cannot be produced out of thin air without any backing value, right? So you don't want issuance to change. You don't want inflation or deflation that is not strictly controlled by some protocol or some rule, right? So yeah, this is very simple on the same chain. And this is what you see most of the time in cryptocurrency. So let's take Ethereum, right? Ethereum is this massive behemoth of a blockchain that seems to do a million things, different things, but it's actually the same chain. It's one chain. It's one chain doing a lot of the same things. And it has all of these different tokens, all of these ERC20, standard defined tokens. But all of the transfers and everything that moves there is still happening on the same chain, right? And it definitely keeps things simple, but it's also very limiting in terms of what you can do, because the whole of Ethereum looks the same, right? The set of things that it's capable of is very limited. And we don't want that in Polkadot. In Polkadot, we want it to be capable of anything and everything in this world that your mind can imagine. And if you have a crazy use case, you just do a crazy app chain or a crazy parathread or something. You don't have to conform, right? You have this heterogeneity. But then you have a problem. Now, within this ecosystem, you don't transfer or you don't move value just from point to point on the same chain. Now you have to move them between chains, move this value or assets or whatever between chains. And we have an example here where chain A and chain B trust each other. What does trust each other mean? It's a teleport example because you use teleports when you have trust. You have Alice on chain A, Bob on chain B, same as before. Now they're on different chains, and they're transferring, or they want to transfer tokens. Tokens is this imaginary asset or token A, right? It comes from chain A. Now, tokens are an integral part of chain A. So chain A's interests are aligned with the, let's say, correct manipulation of tokens in the entire ecosystem. So they don't want tokens to be produced out of thin air. So if chain A trusts chain B, they can do a teleport between these two chains. Users of one part can do teleports, or locations or whatever can do teleports between those two chains. And how does teleport work is that on the source side, 42 tokens are burned, they just disappear. A message is sent to chain B and says teleport 42 tokens. And then chain B mints 42 tokens. This is part of a protocol that they both implement. Now, if you look at the end results, Alice minus 42, Bob plus 42. So the users are happy. It happened. What was meant to happen happened. And then the total issuance locally has decreased here on 42 by 42 on chain A, and has increased on chain B by 42. But the global one hasn't changed. And like I said, it's important that this total issuance doesn't change. Now, maybe you figured out why you need trust here. Is because chain A doesn't verify, what chain B is doing. It just trusts that their interests are aligned in regards to tokens, and they'll do the right thing. So when chain A burns 42 and says, teleport 42, it trusts chain B to actually mint only 42 instead of, minting 4200 and say, I'm minting 4200, and basically I'm diluting some of the value of tokens on the other side for my own personal gains, or from Bob's own personal gains.
Can I interrupt you there, Adrian? Just because please. James has a question here on the chat. Please. So James, if you want to ask it directly, maybe that's better.
I don't see the chat, so please just interrupt me when you have questions.
Yeah, for sure. My question is, how do you ensure that the teleport message makes it to chain B before you burn the tokens on chain A? Is there a scenario where you burn tokens on chain A, but they're never minted on chain B because the message doesn't make it through?
Yeah, that would be a scenario that we call a message error. And there's basically error handling protocols that run afterwards. But in general, message passing, at least within the Polkadot ecosystem, is guaranteed. What do you call it? Reliability, guaranteed reliability. So you have in-order messaging, which is guaranteed, and also reliable delivery of messages. And that is done currently by the relay chain. So between two parachains, messages are sent with this, maybe you've heard of it, XCMP protocol, or HRMP protocol. And that is, some parachain, parachain A says, I'm sending this message. From the point of view of the teleport, once it put it in this queue in its state, this message is supposed to be sent to chain B. It already burns the tokens because it knows that the relay chain guarantees that the message will be actually delivered. So there's no synchronicity there required to go back and forth. And then when that block is verified by the relay chain, as in verifying the execution integrity, the relay chain also basically has this protocol that checks all of the messages in the outbound queue, kind of what messages does this chain want to produce, and then it sends those messages to the block producers of chain B and expects that the next block produced by chain B, or one of the next blocks produced by chain B, to include those messages as having been delivered. Right. So that's how you guarantee that these messages happen. But this is a low-level, let's say, parachain protocol.
Okay, gotcha. Thanks. Yeah, that makes sense. And I guess if the messages don't make it to chain B, then the relay chain can see that that hasn't happened, and presumably some error mechanism kicks in.
Yeah, so no, the message has to reach chain B, as in the message, the parachain or the relay chain will not accept any new blocks on chain B unless, it includes the message, because it's part of the protocol. Yeah. It's like, I told you need to include this message, so I expect that your next block includes this message. It's as simple as that. Otherwise, it's not valid block. So the delivery is guaranteed and will happen 100%. What does happen is that, let's say, errors do happen though on, let's say, higher levels of logic of the protocol, where this teleport is like simplified here. This is an XCM program that does a couple of things next to this teleport. Maybe some conditions are not satisfied. Maybe some fees were not paid. Maybe some barrier was not. Maybe this chain doesn't allow teleports or something happened, right? And then you have an error. And what happens is you burnt it here, but you haven't minted it here. But then you have to think about this error recovery protocols. And most of them are not automatic, because most of the time these two chains trust each other, and the code is audited and verified and works like all the time. When there is a bug, you fix the bug, and then you fix the damage from the bug through governance or something.
Okay, yeah, gotcha. Perfect, thank you.
Now let's look at the same transfer. This time the two chains do not trust each other. What happens is we're using that concept we talked about earlier, which is the sovereign account of chain B. So Alice still loses or sends away the 42 tokens. But then now, instead of them being burned, they're actually transferred to the sovereign account of chain B. And this sovereign account of chain B is controlled by chain B, right? So at this point, you could say conceptually that these 42 tokens are under the control of chain B, right? Because they're in chain B's account, and chain B can do whatever it wants with them. It can send them back to Alice or whatever, right? So from the point of view of chain A, it hasn't sent them to Bob or whoever on chain B. It sent them to chain B, right? And then it relies on chain B to do whatever chain B wants to do with them. Just as before, it says teleport and I rely on you to mint and then send to Bob or whatever. Now it kind of relies on chain B to do the same thing, but doesn't trust chain B to not mess with the total issuance. So what it does is puts them in what we call a reserve. We call it, this is the reserve of tokens of chain B, and says to chain B, I deposited 40 tokens in your reserve, right? So you have this account, the whole of chain B is like, if you think of this as two banks, when you send money from one bank to another, before the money actually moves through or whatever, or let's think about how it happened like in the old days. I'm trying to invent an analogy now. Bear with me if it goes wrong. Like if you had to send gold, physical actual money, right? Gold from one place to another, you could put it in a vault in this side that is controlled by some escrow, basically, and then just tell this other guy, you have control of it over it. You can let your user make use of it before we actually send it physically through, right? In this case, we never send it physically through. So yeah, bad analogy. Anyway, so basically you get this message saying, I have deposited 42 tokens to your reserve. So then chain B, what it does, it mints 42, we call them wrapped tokens, but in practice, so conceptually they're kind of wrapped tokens because they're not the real tokens. But in practice, if you look at across the ecosystem, everybody refers to them as tokens because they're sort of fungible, right? You trust, if you have an account on chain B, you trust chain B that it will mean 42 only if it has 42 in its reserve. And basically now if chain B does something nasty, right? If it cheats in any way, it doesn't create damage for chain A or the users of chain A. It creates damage only for itself and its users, right? So if it's like minting 4,200 tokens to Bob, it only has a reserve of 42 instead of 4,200. So Bob cannot reclaim that value, right? Bob might pass on that scam to some other user on chain B, but that scam is limited. The damage is limited to chain B. It never goes back to chain A, right? And the reputation damage happens on chain B and not on chain A, or the token might take a bit of a hit, a reputation hit, but not as much as in the teleport case where you mess up everything for everyone. So all of this makes sense. Does anybody have any questions? Good. Okay. One other thing to note: the total issuance of tokens hasn't changed here on chain A, right? And now you can see. Now we're back in a case where chain A is in total control of the total issuance of tokens, right? It's not like here before where it's you have kind of a shared control. The global doesn't change, but locals do change. Here, this is the source of truth, chain A. This is the only one that's trusted for the source of truth of Toka. And here, the total issuance doesn't change. So you cannot do uncontrolled inflation or something. We call this concept or whatever as chain A being the reserve chain of Toka. Right? That's the origin and the reserve chain. This is where Tokas always live. And other chains have these sovereign accounts, these derived accounts, which act as reserves. But basically, the value never leaves this chain in concept. Right? In practice, the way you use it is that you actually pass this value to chain B. Chain B uses it. As long as chain B doesn't cheat, everything works fine. And if chain B starts cheating, then it's only shooting itself in the foot. So a little more details on asset reserves or chains acting as asset reserves. Usually it's a single chain, right? The chain that owns the asset, its interests is aligned with the correct usage and issuance of that asset. So usually it is a single chain, but can be more than one chain acting as a reserve. When there are more chains that are acting as a reserve, that usually happens because the interests are aligned. Right? So maybe you have a big company launching two different chains. Right? Behind the scenes, these look like two sovereign chains, and they are two sovereign chains, but behind the scenes, they're controlled by the same body, right? So I provided an example with an external company, but we can talk about OpenGov, right, on chain. And for example, all the system chains are intrinsically aligned because they are all aligned. They are all governed by the same body, by OpenGov. Right? So one chain cannot do something that's against the interests of the other chain in the same kind of trust zone because it's owned by the same group of people. Right? So the interests are naturally aligned between them. Now, assets can and should be teleported within a trust zone. So basically, if you have these chains where the interests are aligned, we can call it, okay, this is like a trust zone. And we can teleport assets within them because we know these two guys will not cheat on each other because their interests are aligned. And then when you want to do cross-chain asset transfers between or outside of trust zones, you do these reserve transfers we just saw. The owner chain is the default reserve location for an asset. It's just logical. And then you can think of what we just discussed and expand the sort of rule and realize that other chains where the asset can be teleported can also act as a reserve. And the reason for that is the level of trust between us is equivalent, right? So if you trust one for a reserve, you might as well trust the other. There is no trust assumption changes between the two. And even more than that, you can think about how the liquidity itself is kind of split between these 2 or 3 or 4 locations. So if you had some ridiculous use case where you want to just get everything, you wouldn't be able to get everything from the original chain, because part of it has been teleported to these other places. So you'd have to get some of it from that reserve, some of it from that reserve, some of it from that reserve, if you wanted to get everything, which is artificial use case, but yeah. And then we come into this interesting side effect, or side requirement, which is any transfer of asset X needs to go through at least one reserve location of asset X. Right? So exactly what we saw before. You have to get it from a reserve location, right? That's where asset X exists, right? If you get it from chain B directly, the actual ownership of the assets are in chain B's sovereign account on chain A. So as long as chain A is not part of the protocol, part of the message exchange, it doesn't know to move the ownership from chain B's sovereign account to chain C. So let's look at this example. I'm talking about that any transfer has to go to at least one reserve location of asset X. So for example, we were talking about Toka that has a reserve location of chain A. So we have between chain A and chain B, one direction or the other direction, right? We discussed step by step how the deposit happens. You put it in the reserve here, and you send a message that it's been set to your reserve. So this chain mints and gives them to Eve. And in the other direction, chain B burns this wrapped tokens, this basically derivative, and says to chain A, please take, not please. It doesn't ask it, right? It sends a message where it actually operates on chain A sovereignly through its sovereign account. So what I'm saying is basically, it's not a message where you say, please do something chain A on my behalf. It's like actually you're calling a function of the code of chain A where you actually have control over this account and do whatever you want with it. And basically what you do is move out 42 tokens and send them to Bob. Right. This is part of chain A logic, like part of the chain A code. But that code only allows the location of B to operate on this account. Right? So that's called the reserve withdrawal. We're withdrawing money out of our reserve and sending it somewhere else. And this is basically point to point where the reserve is actually involved it's either the source or destination. But then there's also a case where it's not involved, right? So now we're zooming out a bit more and saying, okay, Toka is really successful in the ecosystem, and it's not only on chain A and chain B, it's now also on chain C. So you're obviously going to have a use case where chain C, user on chain C wants to send it to user on chain B, right? So in order to actually send this, it has to go through a reserve of Toka. In this case, in this example here, I'm using chain A as like the default reserve. And the way it happens is exactly a combination of these two, what we saw earlier. From C, basically, it withdraws it from its sovereign account and moves it to the sovereign account of B, and then B sends it or mints it to Eve. So basically, you can understand how on chain A, the ownership of these accounts, of these tokens, move from chain C. Why do I have B here? It was supposed to be C. Sorry. So green here is basically, it was supposed to be SAC. So it moves from the ownership of chain C to the ownership of chain B, but never leaves this kind of chain A. And then, chain B can definitely mint and give it to Eve, knowing that it now has ownership of the reserves. So it means 42 wrapped tokens that are backed by the 42 tokens it has control over on chain A. So this is how reserve transfers work.
Adrian, one question here. Well,
please.
maybe a clarification, right? Like here, you were saying, yeah, like for this to work, the remote reserve, it has to go through the actual reserve, right, the chain A. But if in the case that chain C directly, let's say, does a, I don't know how to call it, malicious teleport of token from C to B, I mean, that can happen, right? But this can be considered like a breaking of the protocol of the, let's say, I don't know, the reserve back transfer protocol, right?
Yeah.
Yeah.
So it's not, that's a very good question, a good point to discuss. It's not guaranteed by, let's say, the Polkadot Parachain protocol, like we discussed about messages being guaranteed to go through, but it's sort of enforced, not sort of, it's actually enforced by the configuration of the runtimes of the different chains, right? So there is a XCM configuration part of every chain's runtime. There's two items. One is teleport and is reserve. And it's basically a configuration where some filters are configured for the chain, saying, or like writing in stone, right? Writing in the code, in an invariable of that chain logic, which are the locations that are allowed to teleport which assets, and which are locations which are reserves for which assets. So basically, it's kind of a matrix. You can think of it as a matrix. In reality, it's more like a filter, so you don't have to use up memory with actual matrix values. But you can think of it conceptually as a matrix. For this asset, I can accept teleports from this location, and then this asset I can accept its reserves are this, and this location. And the way that is populated, so in your example, we're talking about chain B, and chain B will not accept a teleport from chain C. And the reason it will not accept it is because the developers of chain B, the people, the body governing chain B, do not want to allow such a teleport because it knows that basically chain A is the source of truth for token. So if it allows teleports coming from chain C, it's basically allowing this teleporting of these, wrapped tokens that have no real value unless you also have the reserve behind them, right? So if you do a teleport directly on chain A, the actual tokens never left the green reserve bubble here and moved to the red reserve bubble here. So what happens is chain B, if they were to accept that teleport, they would mint this 42 wrap tokens out of sort of thin air without having the control over the reserve on chain A. So basically, it doesn't have the backing value, right? It's like the US government printing money without having any backing behind it, right? You just create inflation that ends up hurting your users. Does that answer your question?
Yeah, perfectly. Yeah.